Hello everyone. Now we're going to look at how to properly name different part of a wave. Now let's look at a transverse wave as an example. So here I have a transverse wave. Okay. So a transverse wave is going to have a few things that we need to identify. For example, medium, which is what type of material the wave is actually traveling in. Now remember, we are talking about physical wave in here. I mean, that question is going to be vacuum if you're talking about electromagnetic wave. But, let's say we have a sound wave, or we have a earthquake wave, water wave, people wave, wave on a slinky, wave on a rope, then it's the material. Medium is the material that the wave travels in. Now, then in a wave, you will always be able to find somewhere that has the highest altitude, the highest point, and that is called the crest. Okay, the crest is the point with the highest location. Now, so in here, where would the crest be? The crest, you can say this is the crest. Of course, you can also say this is the crest, right? If this is a for example, a periodic wave, it might have like many crests, right? Now, then the lowest point on the wave is called the trough. So the trough of this wave, for example, would be over here. Okay, or over here if you want, like over here on this side too. But of course, you don't have to label like every single one. If I ask you to label a wave for me, or if they give you a multiple choice question and ask you to just pick one. Okay, all right. Now, another thing that we need to know about describing a wave is amplitude. Amplitude. Okay, so amplitude is the maximum displacement from rest, which is, displacement, it must be a distance kind of measurement, right? So yes, it is. It is measured in meter. Okay, amplitude is measured in meter. So how much does the rope actually go up and down? Now, in this case though, amplitude, for example, is not, okay, which is really easy to get confused on. A lot of time, people will mistake this as amplitude, and that is wrong. Okay, amplitude is the maximum disturbance from the middle. Okay, from the middle. Now, the rope, when it's at rest, when no one is moving the rope, where's the rope? The rope, when no one is disturbing it, should just be like this, right? So the maximum disturbance is from that point, which is what laterally is the rope's location, to the maximum point. So the amplitude is actually here. Okay, this is the amplitude. Now, of course, it will be exactly the same thing if you measure from the middle to the lowest point. That is also called the amplitude. So it doesn't matter if you're measuring from the top to middle, or from the bottom to the middle. The amplitude should be the same. Okay, doesn't matter where you actually measure it from. All right, amplitude. Now, the next thing, usually speaking, a wave with higher amplitude carries more energy. Okay, so for example, if someone, if you have someone making a very soft sound, then the wave looks like this. But if someone is making a very loud noise, then the wave looks like this. So which wave carries more energy? I know sound wave is not a transverse wave. I know that sound wave is a longitudinal wave, but it's almost impossible to draw longitudinal wave by hand. You literally have to draw like the slinky getting closer and wider at a different point, right? So it's really difficult to draw. But someone moving for example, a rope up and down, right? Making those two waves, wave A and wave B. Which one needs more energy to generate? Obviously wave B, right? Because you have to move your hand up and down for a larger amplitude. So it's more difficult to do that. It costs more energy to do that, right? So waves with high amplitude carries more energy. Hopefully that makes sense. Okay, so last but not least is the wavelength. Now, this is sometimes a confusing concept, because if a wave can be, like for example, those periodic wave, right, can actually last forever. I mean, how can there be a length? Because isn't the length infinite? Well, that's true. I mean, if you're talking about like so for example, if someone is making like a small wave like this, and someone's making another wave like this, they can both be, lasting for forever, right? I mean, how can you say which one has what length? So in order to make that communication actually, make sense, we classify the length of a wave to just the length of one cycle. Now, what is one cycle? When you have a point, for example, this pink point in here, to another point on the wave that repeats itself, this is one cycle. So this is one cycle. Okay, so from the first pink point to the second pink point is one cycle of a wave. Now, one cycle of the wave, the length of that, well, okay, we're talking about the length, so this must be another distant measurement, right? Yes, it is. It's measured in meter. So wavelength is measured in meter. This is called one wavelength, like one length of that wave. Now, what symbol do we use for wavelength? Well, we actually don't use an English symbol. We use a symbol called lambda. 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 L-A-M-D-A. Lambda. Lambda. Lambda is not English, of course. It's the Greek symbol from Greek, and it is their version of L. And that it's like if you know Chinese, this is actually the character, the Chinese. It looks exactly the same as the Chinese character of coming into a room. Like if we try to invite someone to come into a room, then this is the character that we will use. If you know Chinese, you know what I'm talking about. If you don't, you learn something new today. So how do you write it? Is like this, and then like that. Okay, lambda, lambda. Okay, so wavelength, the symbol that we use in our equation is this lambda character, and this is one wavelength right here. Now, you don't have to measure the wavelength from the middle to the middle. You could measure the wavelength from the crest to the crest. And if you measure it really carefully, you will find that this lambda is the same lambda that you measure from the middle to the middle. You can even do trough to the trough, like the bottom to the bottom. It should be exactly the same. Now, if you don't trust me, I will highlight this and I will try to overlap it to the other one. Look, right? They're exactly the same. So any point of the wave to any other point of the wave will always, like, as long as they repeat. So from the crest to the crest, from the trough to the trough. Now, what is one thing that one mistake that a lot of students will make is they will call like this and this one wavelength. And they will say, but Mr. Chang, this is the same point, isn't it? Like you said, just go pick one point on the wave and wait until you have the same point again. But these two are not the same point. You see, the first point on the left hand side, the wave is going downward to the right hand side, right? But the second point right here, the wave is going upward to the right hand side. So they're not physically the same point. Now, what will be the same point is this one and this one is the same point. Because on the first point on the left, the wave is going up to the right hand side from bottom left, right? Bottom left to upper right. And in the second point on the right is also, the wave is also traveling from the bottom left to the upper right. So these 2 points are exactly the same, but not like this and this, for example. So they won't give you the right wavelength. So you can measure the wavelength whichever way that you want, as long as it is from the same point. Now, it can even be like from here to here, for example, and that will be the same wavelength. So you just need to take a ruler, measure the length of it, and it's called a wavelength. Okay, so this is called a wavelength. Now, okay, so let's put that in here, right here. So you can have a wave with different wavelengths. So maybe you can have a wave that looks like this, okay, or you can have a wave that looks like this with a shorter wavelength, okay, or you can even measure a wave with the wavelength from the crest to another crest. So from the crest to another crest though, from the crest to the trough is only half. You will have questions like this. So that's one wavelength. For this one, it will be like one wavelength. For this one, it will be like one wavelength. Okay, so if a question gives you the distance from the crest to the trough, like they say, oh yeah, the distance between here and here is 10 cm, then what is the wavelength of this wave? 20 cm, because you have to go to the crest again for it to be one complete wave, right? So this is the wavelength, and the wavelength will be 20 cm. You will see questions like this. Okay, so now, generally speaking, waves with shorter wavelength have more energy. Shorter wavelength has more energy because a wave with shorter wavelength is actually more difficult to generate. Think about it. A wave with long wavelength, you don't have to move your arm very rapidly. Now, we're not talking about the amplitude of your arm movement. Now, we're talking about the frequency of your arm movement, how fast you need to move your arm. Now, you know that in order to generate the wave that I'm circling right now, you need to move your arm more rapidly than the one that is on the left, right? So which one costs more energy to actually generate? The one that has shorter wavelength. Therefore, it carries more energy to the other side. You're moving the stuff more rapidly. Of course, it carries more energy to the other side. So, for example, the difference between, let's say, visible light, which is not harmful to human at all, compare that to gamma radiation, which cause all sorts of cancer and people die from it, is the wavelength. Like if you look at the difference between visible light, which is a radiation wave, and you look at that of, let's say microwave and gamma radiation and UV radiation, the difference is all these other waves that are more harmful have shorter wavelength. Actually, if you look at the list in here from the last page of notes, and you look at all of these radiation, the group of radiation, they are actually listed right now in descending length, descending wavelength order. So radio wave has a very long wavelength. That's why you never heard someone getting sick by radio wave. Like you don't say, oh, I got a lot of radio wave, I'm getting radiation burn, I'm dying. No, that doesn't exist. Radio wave is all around us. You just need a radio to capture it, and you can listen to the radio podcast, right? Radio wave is all around us, and it has been for many, many years, and no harm effect is done to us. Infrared radiation, shorter wavelength already, and that can heat up food. You see, it's already doing some damage. Microwave can actually cause water molecule to vibrate rapidly inside your food, and that's what heat up your food. See, causing more damage. Visible light doesn't cause damage to us, even though it is physically smaller than, the wavelength is physically smaller than infrared and microwave, because that's because of only one reason though, because we adapted to it. The reason why visible light is not harmful to human being is because we are a species evolved on Earth, and Earth gets its energy source from only one object, the sun, and the sun produces all of these radiation, actually all of them, and send it to us. But they are not all equally abundant though. Our sun produces very little of anything else, mostly visible light. Our sun produces most of its energy in this visible light wavelength. Yes, it does produce radio wave. Yes, it does produce infrared radiation and ultraviolet and X-ray and gamma radiation, but not all of them at the equal amount. So let me give you an example. Like I think our sun produces like 70% of its radiation in visible light, and the rest of the radiation only in very small quantity. Gamma radiation in very small quantity, for example. So any species that are evolved on Earth must have adapted to that radiation, visible light, really well. Otherwise, we will die before we get to this point, right? The species go extinct before it gets to this point. Like imagine you creating a new species on Earth, and that species is like very susceptible to visible light and is lethal to them. Then how on Earth could that species even be evolved on Earth for like millions of years? It should have been killed by the single most biggest power source that we have, which is the sun, that send us like 70-80% of radiation in visible light spectrum. Now, ultraviolet radiation has smaller wavelength, that's why it causes skin cancer. X-ray has even smaller wavelength, that's why it doesn't even cause skin cancer. It can cause skin cancer and then bone cancers, and various other type of cancers too. And gamma radiation just gives you a cocktail of cancers. right? And because the gamma radiation has the smallest wavelength out of this entire group. Okay, so it's like an assassin, but in this case, a family of assassin, but in this case, the smaller the size they are, the more damage they will do. Now, by small, we don't mean amplitude. By small, we mean wavelength. Smaller wavelength waves are more deadly, are deadlier than large wavelength waves. You can almost think about it as, if an elephant is charging toward you, you can see the elephant coming, so you run away, right? But a very small, fast traveling bullet is much harder to dodge. Okay, so sometimes I think about it like that. It's like, why does shorter wavelength carries more energy and be more deadly? Is because they are smaller and it's much easier for those radiation or wave to get inside you and cause damage. Okay, if it's like a very large wave coming at you, you can usually see it from miles away and say, hey, there is a T-Rex over there. Let's, run away, jump into our cars. But then if the T-Rex is like the size of a mosquito and then it's flying at very fast speed, then you go, by the time you notice, you already hit. Okay, now let's go back to our wave structure. So you should have this picture labeled like this. And when I ask you to label a wave, you should be able to label everything that's on this picture with you right now. Okay. Now, two more definitions, and then we'll get into some calculations. Another term that you should know about wave is, I think I mentioned that word already, frequency, which is how fast you're moving the system, right? How fast you're moving the system. Now, frequency is defined as cycles, the number of cycles that you go up and down per second if you're making a transverse wave. If you're making a longitudinal wave, it's how many cycles of back and forward you're for example compressing the slinky every second. Okay, so the unit for frequency is hertz. Hz, right? So that's a shortcut, but it's actually hertz, like this. Okay, so what is 1 hertz? 1 hertz, okay, is 1 cycle per second. So if you're tapping, so for example, let me show you. 1 cycle per second. So for example, I'm tapping my hand on the table, on the microphone right now. About 1 time a second. Hopefully you can hear it. Maybe if I tap at the front, you can hear it. So that will be a frequency of roughly 1 hertz. So 2 hertz means 2 cycles per second. So it will sound something like this. Like 2 taps per second. So 3 hertz, 4 hertz, 100 hertz, like you get the idea, right? So so the higher the frequency, the higher the frequency, the shorter the wavelength, and the more the energy. I mean, obviously, higher frequency, more energy, because you need to spend more energy if you want to move faster, right? So for example, if you see 8 waves, so there's an example right there, 8 wave passes you in 2 seconds, what is the frequency of your wave? And that is a simple thing to calculate. So the frequency is the number of cycle, which in this case is 8, passing by every 2 seconds, so that's a 4 hertz. So that's 4 hertz, right? Okay. Now, moving on, the last one of these definition is, by the way, frequency, we use the symbol f, lowercase f, to represent in our equation. So if you see an equation with f in it, that is for frequency. Period is a time measurement, and we usually use capital T, so it's time per cycle. So that's exactly the reciprocal of frequency. So that means, hey, how many seconds for each cycle? So instead of how many cycle per each second, it's how many seconds per each cycle. So the unit for frequency is actually, the unit for period is actually seconds. How many seconds for each cycle? All right. So for example, the wave in the last example is every 2 seconds, I think. So instead of writing the cycle first, 2 seconds for every 8 cycles, 8 waves, right? 8 waves, 8 cycles. So that means the period is 0.25 second. Okay, so 0.25 seconds. So that's the period. That's the time that it takes for one wave to pass by. Okay, the time for one wave. So if you look at the definition of frequency and period, then it's obvious that frequency and period is just the reciprocal of each other. So you can say frequency is 1 over period, or you can say period is 1 over frequency. I don't think these two equations is on the formula sheet, but they're kind of like a definition thing that you should know. So if you want to include it in the wave sections on the formula sheet, go ahead. Now, this just gives you a quick way of converting frequency to period and period to frequency, as long as you make sure that the unit is in hertz for frequency and seconds for period. Sometimes you'll find questions that give you, for example, frequency, but then you lead period to do something. So you need to convert the frequency to period first, and then you continue. So that's why you use it. Give you an example. So, for example, if you play instruments, like pianos or guitar, the middle C on a piano produces sound with a frequency of 256 hertz. Now, what does that mean? That means if you have a very advanced microscope and you can actually see the string on the piano. Now, I know piano looks like, you're just pressing a key, right? But have you ever actually go inside and open up the piano to see the inside of it? Now, of course, it's different if you have an electronic piano. I do understand that. But I'm talking about like a traditional piano that actually has like a internal mechanism. If you open it, you can see strings inside. There are actually strings inside. So piano is actually a string instrument. Yeah, it's not a, like if you open it, there are strings inside. So when you hit one of those keys on the pianos, right, for example, middle C, then actually what happened is the motion of you hitting that key is going to vibrate a string inside, a certain string inside. And that string vibrates in a frequency of 256 hertz. What does that mean? 256 times movement every second. So the air molecule will also, next to it, will also vibrate at 256 times every second. So what's the period? If they give you frequency and you're looking for period, just looking for one of those inverse equation like this. So if it's 256 hertz, then, you do 1 over 256 and you will end up with 0.039 seconds. Okay, so this is the period of the middle C in the piano. Now, you might have seen the word hertz earlier too. I mean, if it's the first time you hear about it, I'm pretty sure that you have seen it before. Like CPU speed, like on your computer, they're in like gigahertz, megahertz back in the day, but now gigahertz. Giga means billion. Gigahertz just mean billions of hertz. So when they say, my CPU has a speed of 2.4 gigahertz, what does that mean? That means your CPU can do 2.4 billion cycles of calculations every second. Remember, 1 hertz is 1 cycle. And in a computer, what is 1 cycle? 1 cycle is actually 1 calculation. When I say calculation, I don't mean exactly as, doing a 1 plus 1, but, in terms of computer calculation. I mean, I won't go too much in detail for that. Like, I will just give you an example. For example, if you actually want to do a calculation of like 1 plus 3, it requires multiple steps. It might require like 4 or 5 steps of computer calculation to get that done for you. But in short, you can think of the computer has the CPU of a computer. The higher the speed of the CPU, the more it can do at the same time. So for example, a computer that has a 1.5 gigahertz CPU versus a computer that has a 3 gigahertz CPU, the 3 gigahertz CPU will be able to do the same task at half the time because it has the capacity, theoretically, right? It has a capacity to handle twice as much information every second. Okay, so remember, the next time you shop for computer, that's what that number actually means, right? They say, it's a 2.4 gigahertz and this other one is 5 gigahertz. Well, obviously the 5 gigahertz one is going to be a lot faster because it can do 5 billion calculation per second versus 2.4 billion calculation per second, right? But of course, it's going to cost you like a fortune too. It's going to cost you a lot of money to buy them. Okay. All right. Now, the next thing we will talk about is how fast the speed is moving when it's transmitting. In general, the speed of any wave going through a medium is fixed. Okay, so the speed of a wave going through the medium is fixed regardless of the energy of the wave. So what does that mean? That mean what is the one example I can show? Oh, like here you go. Talking louder doesn't actually make the sound go faster. So when you're yelling at people versus just like talking to people, it doesn't make them hear your voice faster. The energy of the sound wave doesn't go faster because you have more energy in it. So the speed of a wave through a medium, for example, the speed of sound wave through air is fixed, no matter like how loud the sound is. So in this case, right? So for example, sound wave always travel at roughly 343 meter per second in room temperature. So sound wave actually depends on temperature, because different temperature makes different air, right? If the temperature is really hot, the air molecule will actually be further apart compared to if the temperature is really low, then the air molecule is actually more dense. I think this type of different density of air depending on temperature is something that you are already familiar with, but that will actually affect the speed of sound, because the speed of sound depends on those air molecules to actually travel from one point to another. So when you have air molecule that has different density, it will affect speed of sound. So when we say 343 meter per second, that is only on room temperature. We do have an equation that can calculate the speed of sound later on in this chapter. Now, so assuming that you're at room temperature, regardless of its pitch, that means the pitch of a sound is its frequency. So regardless of its frequency, or volume, which is how loud a sound is, which is the amplitude. So for a sound wave, right, the frequency is its pitch. High frequency, high pitch sound. Low frequency, no pitch sound. Amplitude is its volume. But it doesn't matter if you speak in a high pitch or low pitch sound. It doesn't matter if you speak in a loud amplitude or a soft sound, loud sound or soft sound. The speed of sound is exactly the same. It only depends on the type of gas that it's going through, and it also depends on the temperature, but it has nothing to do with the frequency of sound or the amplitude of sound. Now, however, in solid steel, a sound wave, like a longitudinal wave, will always travel at the speed of approximately 5,790 meters per second. So in solid steel, a sound wave can actually go like 15 times faster than air. So a sound wave going through solid is actually faster than a sound wave going through air, which is surprising, but not really surprising. That's the reason why, if you're ever trapped underground and people trying to search for you in the wreckage, one of the best things to do is to hit the whatever like metal surrounding around you or rocks around you. The best thing to do to get someone to notice that you're underground is by hitting some solid structure next to you with something that you have handy. So for example, you can pick up like a piece of metal and start hitting other metals next to you, just repeatedly hitting it. Then, because sound wave traveling through solid can go further and faster than sound wave going through air. So if you're trapped underground, it's very unlikely that your calling for help voice, the sound wave, can actually go through all the wreckage and go outside by air. It's very, very unrealistic for that to happen. But for example, if there is like a beam, right? So if there is like the structure has like a metal beam inside, and the metal beam happens to be next to you, and the other end of that metal beam happens to be on the ground level, right? Then by you by taking like another piece of metal, hitting that metal beam, it's going to make a sound that actually travel very, very quickly to the surface. And it can also go much, much further. So people, hopefully the rescue team, is going to walk by this metal beam that's sticking out on the surface and notice, hey, how come there's like this rhythmic a sound coming out from it, which is not natural, right? Because the natural thing, for example, drip of water or whatnot, doesn't give you like a rhythm. Like you should make like a special rhythm, like duck 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 duck. This is not natural. Then people will know if we follow this beam and keep digging, we will get to someone, right, who is alive, and let's save him. So that's how you can get rescued, right? So knowing physics in that type of situation will help you. Now, so this is for a longitudinal wave, which is what happens if you, for example, hit a surface, you compress it. On the other hand, if you make a transverse wave in solid steel, the transverse wave will travel at approximately 3,000 meters per second. Now, you don't have to memorize these numbers, of course, like how fast the sound travel in steel, and that's not something that I want you to know or remember. You just need to know that they go pretty fast, faster than air, actually. Okay, so now the change to the composition, so the different type of material is going to affect the speed of the wave transmitted in it. The general rule is that with all things being equal, the higher the rigidity, that means the more solid something is, means faster wave travel. Higher rigidity, faster wave travel. That's solid. Okay, so solid wave can travel faster in solid compared to in liquid, and liquid is faster than air. So technically speaking, the speed of sound in the air is the slowest that it could be. Speed of sound in water is faster, and speed of sound in solid is even faster. Okay, so in the air is already very small. Okay, so now the reason why, though, when you think about it, is actually quite straightforward. I mean, if the system is more rigid, for example, like a solid piece of rock, that means those molecules are closer together to begin with. Then, in that case, moving one molecule will affect its neighboring molecule much more rapidly because they are already close together. Whereas in air molecule, what happens is that air molecules are very far apart to begin with. So even though you are trying to disturb the molecule from one end, it takes time for that disruption to travel to the next groups of air molecule next to it, because there are huge gap in between that the air molecule has to go through. Whereas in a solid or liquid, those molecules are closer to begin with, so you affect one end. Like, for example, so compressing the air, so you can use your hand, make like some kind of an air wave. Air wave is a sound wave, right, technically. So you can make an air wave, and you will notice there's a delay. So try to make an air wave against your face. So by moving your hand up and down and make an air wave pushing your face, you notice a small delay between you moving your arm and the air hitting you, right? Because the air takes time to go to you. That's like the sound taking time to go to you. Now, but if imagine that you have, so you must have a pencil nearby right now, right? Put your pencil on the table and try pushing that pencil from one end. You see, when your finger touches that pencil from one end, the other end of that pencil almost moves immediately, right? Because it's a solid object. So imagine this vibration of the pencil moving is a sound wave. So sound wave almost moves instantaneously through metal. Now, of course, or through solid. Of course, the effect is actually not instantaneous. If you have like a very fast speed, well, I mean, yeah, I don't think even a fast speed camera can capture that, but it's a lot faster than like air molecule going to you. Okay, so now how do we generate or how do we actually calculate the speed of a wave? Now, okay, well, remember, speed or velocity is distance over time, right? Okay, so now let's look at the wave. Initially, that wave is over here. This black object is the wave. Now, a few seconds later, that wave is going to go to here. Okay, so I hope you agree. Okay, so the wave is going to go to here in a moment. So, how much time does it take Now, the time it takes for the wave to go through one cycle is called, well, it's called the period, right? That's what the period is. It's the time for one cycle. So that's the period. Okay. How far did it travel? It traveled, so let's look at this point, which is later on this point. So the wave traveled from here to here. Oh, wait a second. This thing is one wavelength, isn't it? Yeah, so the distance traveled is one wavelength. So the wave traveled one wavelength in one period. Okay, so then we can modify this equation. Distance is one wavelength. Time is one period. So the speed of a wave is wavelength divided by period. Okay, that makes sense. But you know, I don't really like dividing stuff. I mean, dividing is no fun. Multiplying is fun. So can we make this equation better? Yes, we could. Do you remember frequency? I know I'm forcing it. Remember, frequency is 1 over period, right? So we can actually replace this 1 over period thing with frequency then. So then, the wave equation is now complete. Ladies and gentlemen, the equation that can calculate the speed of a wave is wavelength times frequency. This is called the universal wave equation. This equation can be used to calculate the speed of any wave as long as you know two things. The speed, the wavelength, which is measured in meter, and the frequency, which has to be measured in hertz. And you'll be able to get the speed, which is of course measured in meter per second. All right, so pretty straightforward. So you need to know the wavelength and the frequency. Now, what if the question gives you a frequency that's not in hertz? For example, what if the frequency is in gigahertz, in kilohertz? Then you have to know those prefixes, right? So for example, kilohertz is times 1,000, kilo is times 1,000, mega is times 1 million, giga is times 1 billion. So you have to know those prefixes and then you can change it back. So for example, this is 30 times 1,000, right? So 30,000 hertz. Right, then you use that equation with 30,000 hertz. Don't put 30 in it. Remember, physics equation can only work if your symbols, if your units are exactly the right units, which in this case is meter for the wavelength and hertz for the frequency. So if you have something else, you have to change it back. All right, so going down to here, let's just do two very quick example. So you have an air horn with a frequency of 220 hertz. If the speed of sound in the air on that day, okay, so now you look at this number and you're saying, hey, this is not the 343. Now remember, that's because it changes, right? Remember, it depends on the temperature of the day. So this number is actually on a very cold day. You later on we'll learn that equation, but for now, just to know that the lower the air temperature, the slower the speed of sound is. Okay, the lower the air temperature, the slower the speed of sound. So this is like a below, like freezing zero degrees Celsius day. So that's why the speed of sound is slower. What is the wavelength of the sound? Okay, so that, all right. So we have a speed. So now speed is equal to wavelength times frequency. We do have the speed in here. So 330 and meter per second. So that's equal to wavelength times the frequency, and frequency is 220 hertz. Now the unit of everything works out in here perfectly. So now we just divide both sides by the 220 and we'll get the wavelength 1.5 meter. Okay, so wavelength is 1.5 meter. All right, now let's look at another one. The distance between successive crests in a series of water waves is 4 meters. Now they're claiming that there are a series of water waves like this, and successive crests means if you look at one crest compared to another crest, next to it, the distance between them is 4 meters. Okay? and the crest travels 8.6 meters in 5 seconds. Now, what does that mean? That means if you look at the crest of the wave, the 5 seconds later, it would have traveled 8.6 seconds because this entire wave is moving to the right hand side. And it's going at 8.6 meter in 5 seconds. So this we can use with our very traditional distance velocity equal distance over time. So the wave covers 8 seconds in, 8.6 meters in 5 seconds. So how fast is the speed of a wave? So we don't have to use the wave equation yet, right? We don't have to use the lambda f yet because, hey, if they tell you exactly how fast the wave is moving, well, then that's even better. Then just use the basic equation from kinematics, right? So distance, 8.6 meter, time is 5 seconds. So therefore, the speed of the wave is 1.72 meter per second. Now, what we want to do is the frequency of a block, the frequency of this wave. So we have what now? We have the speed. Do we have the wavelength? So we do have the speed. Do we have the wavelength? Oh, that 4 meter looks like the wavelength. Yes, it is. From the crest to the crest is also a wavelength. So that is a wavelength, which is also a meter. Wow, perfect. We have everything. So now, lambda f. So speed, 1.72. So we are using the kinematics, one of the kinematics equation to get the speed of the wave. And then we do have the wavelength on ourselves. And we're looking for the frequency. So times f, and the frequency is the unknown. So divide both sides by 4, and we're going to get the frequency, which is 0.43 hertz. Okay, and then that's it. So the equation that you learn from kinematics are still useful even today. Okay, so there is a worksheet attached to that, and I will assign the questions on the post. All right, that's it for this session. Goodbye.